For those of you that don't know me, I'm Steve Sandler, and I am the founder of Picotest, and I'm very active in the world of power integrity. And currently, it seems like everybody wants to be talking about AI data center and HPC, and in particular, the challenges and solutions that we have around power integrity. So that's what I'm going to be talking about today. And one of the things that's really interesting about the AI data center in HPC space is how fast it's growing and scaling. And because of that, we're facing, I think, more challenges in that arena than in many others. And these challenges are in different places. And I'm going to talk about all of them today, but certainly printed circuit board design, cooling, SIPI, and measurement. And I think all of those are presenting challenges. And as the core domain currents are now up to about 2000 amps or so, we've reached the limits of many of the measurements and techniques and skills that we've acquired over the last decade or so. And I think that's where many of the challenges are coming from. And it's also spurring an awful lot of innovation. And so today I'm going to talk a little bit about all of those different things. And so, kind of, here's our agenda. We need to understand where it is that we are. What is the current state of the art, and what are we worried about for the next generation? And generations are happening really fast. So, what do we need to be planning for? A lot of the challenges are PCB related, and so I want to talk about those challenges and how we're working to mitigate them, and in some cases, how we don't know how to mitigate them, but maybe are just crossing our fingers. Some of the measurements that we've learned to make and that I've been teaching for decades that don't work in the current space, the current state of the art. And so, what are we going to do about that? What are we doing now? And what are the shortcomings? And what do we think needs to happen next? There's a lot going on in VRM design and topologies, and there's a lot of reasons for that. But it's kind of interesting because there are so many to talk about. So, we'll talk about that. And of course, all of this electronics requires cooling, and there's an awful lot going on in cooling. And of course, we are going to make sure that we have time for questions in the end. So save your questions because I really like hearing them. We have to start by understanding where we are. And I think that's essential to understanding the current state of technology and also the basis for where it is that we're going to be shifting from, right? We need a good reference point. The current core power rail for AI data center and HPC is sitting at roughly up to about 2200 amps, and that's occurring in a package size that's about 5600 millimeters squared. The typical operating core voltage is between zero point 0.7 and zero point 0.8 volts. And most of these designs use a two-stage lateral power delivery system. And by lateral, I mean that everything is on the same side as the ASIC. It's not backsided power. And this board in the picture, this is one of Picotest's demo boards, and you can actually see the two stages. Just above and just below the ribbon cable, you can see the two big, large power blocks, and those are the 48 volt to 12 volt converters. And then around the ASIC, you can see all of the little power modules, and those are 12 volt to zero point 0.8 volt modules. And then there's a digital controller that's on the far right side of the board. And this is what these HPC data center boards currently look like. And this doesn't mean that that's the maximum current. We are seeing boards as high as about 11,000 amps. We've seen 2,000 amps in much smaller packages than this. And yes, we have seen some 0.55 and zero point 0.6 volt core power rails. But this is kind of a current average state of the art is 2,000 amps, zero point 0.7 to zero point 0.8 volts. And this is moving really fast. So if we just look over the past year, Picotest introduced our first 2,000 amp tutorial at DesignCon about a year ago. Um, and in that session, we showed our board, which is a relatively large board. That one's about 14 inches by 14 inches, if I remember right. And you can see all the power blocks around the ASIC. That ASIC was 100 millimeters by 100 millimeters. And we did the first tutorial with that. It was really popular. 6 months later, that board had already shrunk down to something about the size of the new Hopper NVIDIA board, which is more like around 7 by 10 inches. Same 2000 watts, just much smaller. And the ASIC was still around 100 millimeters by 100 millimeters. And 6 months later, the board was the same size, but the ASIC had shrunk to 75 millimeters by 75 millimeters, or in this case, I think it's actually 72 millimeters by 75 millimeters. And it's still shrinking. Currently, we're seeing 2000 amp boards now at 50 millimeters by 50 millimeters. And so this is one of the challenges that we're facing is just that things are moving really fast. And just as we think we nailed it, it changes. So one of the questions I get a lot is, where does it stop? And the answer is that unfortunately or fortunately, depending which side of the line you're on, it doesn't. It just keeps going and going and going, sort of like the Energizer Bunny. We've actually even heard about 2000 amp chips that are 25 millimeters by 25 millimeters. And we've heard that the new Cerebras wafer is at 33,000 amps. So it's not going to stop. It's just going to keep going. And our job as engineers is to try to figure out how to keep up and just keep supporting it. And so that's our role, and that's what we do. But it does create a lot of challenges. And the challenges in these four major areas: printed circuit board challenges, measurement challenges, cooling challenges, and VRM challenges. And they are all interrelated, but I kind of grouped them into these four categories for us to be able to talk about, starting with the PCB related challenges. When we look at the physical constraints, these boards are super impressive looking and they're also crazy dense. This one happens to be Intel's Gaudi, and you can see the power modules all along the top edge and bottom edge of the board, all those little power modules and all the decoupling caps. And you can see that most of the board is taken up by the GPU. And then there's other power supplies and logic and all that stuff around it. Um, Now, most of this is ultimately going to be covered by a cooling manifold that's going to come down on top of this chip, and it's going to cover the majority of this board as we run liquid cooling through it. And this causes a few problems. One is that there's not a whole lot of access for testing. You don't see many test points on this board. So even getting a probe in here to make measurements is relatively difficult. And even if we could probe it, most of it's going to be covered by a manifold. There are a lot of trade-offs that are occurring in here too, in order to satisfy both the PI requirements and the SI requirements. And all of that comes down to how it is that we get this power um, across the board, really. The number one concern that we hear within the printed circuit board is crosstalk. And this is true of almost every customer that we've talked to. Certainly every customer that's purchased one of our high-speed loads, we've asked the question, what's your goal? Number one is crosstalk. And the concerns of power rail to power rail, power rail to signal. But as with the power goes up, we have higher DIDTs, and the package is getting smaller, so those high DIDTs are getting closer together. And to add to that, um, these customers are starting to design boards now, but they're a long way from actually having ASICs. They might be a year, 2 years, even 3 years out from actually having a chip. And so the question is, how do we assess performance at high speed and look at these issues like crosstalk long before we actually have a chip available to do it? And that's kind of one of the issues. There's another problem, and this was talked about at DesignCon 2025. Brian Hostetler from HPE, I've known Brian a really long time, really brilliant young guy. And one of the things that he gave a paper on is how do we balance the current densities in the vias? All of these BGA balls behind the ASIC, they're all carried through vias, and how do we make the vias share? And that is a huge problem. And he gave a great paper on that topic. But in addition to the fact that we need those currents to share, Typical IPC guidelines are around 2 amps per via, of course, depending on the size of the via and whatever. And currently, our boards are running between 4 and 16 amps per via, and customers are really pushing us to get to 32 amps per via. At the same time, because of the size of the vias, we can't get wall thicknesses more than maybe up to maybe 2 mils, a good day if we're lucky. And so one of the big concerns is what's the reliability of the via, especially in things like, thermal shock and cycling. But we're really crazy high currents and we're about to double them again. And certainly that's one of the bigger concerns. There are thermal challenges. And when you look at these boards, there's not a whole lot of space. And when you look at the losses in the board, um, they're really considerable. These boards typically run end-to-end efficiencies on the range of maybe around 60 or 70% efficiency. So a 2 kilowatt board at 60% efficiency means that we're losing about 1200 watts total. Of course, a big part of that is in the ASIC, but then there's also, a couple hundred watts in power modules, and there's even more than 100 watts in the printed circuit board planes. And so one of the challenges is how does that heat flow? And it kind of flows everywhere, right? The thermal resistance, the heat from the ASIC, well, that's kind of sucked up into the water cooling manifold. Board losses kind of get sucked up through the ASIC and go out through the top also. And there's flow of power everywhere. And so the question is, what do the temperatures look like? How do they become centralized and how do we manage them? One of the ones that probably became really popular because we heard so much about it at the time was NVIDIA's power connectors that had a tendency to melt. And yeah, there's, an awful lot of power in the connector interfaces too, just through contact resistance. And so all of a sudden we have all these thermal challenges that are much bigger than what we're used to also. And those are things that we need to be worried about. Um, and a lot of this is electrothermal. So because the things are running hotter, that affects the thermal performance. And then the thermal performance affects the electrical performance. And then the electrical performance, well, that impacts the thermal performance again. So we end up with this interactive thermal challenge. And that's requiring us to do a lot more electrothermal simulation. In fact, we're doing a lot of that in PE Pro now, where Keysight did add electrothermal simulation, so we can do that just part of our power integrity analysis. And then we get to measurement challenges, and a lot of what I do is measurement focused. A lot of what Picotest does is makes measurement tools, probes, adapters, and so on and so forth. And so we're kind of front and center in dealing with some of these measurement challenges, which are not trivial. One of the bigger problems is, the power planes now are well below 30 microns. We're seeing 10 micron planes. A year or two ago, we were talking about 100 microns. The difference between 100 microns and 30 microns is in our ability or inability to measure it. So at 100 microns, we were still able to measure printed circuit board PDN impedances using a vector network analyzer. When we get down below 30 microns, vector network analyzers don't have enough source power to overcome the power rail noise. Even using source power amplifiers, we can't get there. In fact, I'm going to give a paper on this next week or 2 weeks from now at SPI on how we're going to measure impedance of these high power boards below 30 microns. And we're doing that using time domain FFT data. And here you can see on the right side, we're using one of our high-speed transient pulsars to generate impulses. And then on the left side, you can have FFTs of the voltage and current waveforms. And then we can divide voltage divided by current, and we can get impedance. And one of the benefits of doing it this way is that we can do it incredibly fast. And another benefit is that the currents are really large. Even using these impulses, you can see that the fundamentals down in that lower right corner, we get about a 30 amp signal. And you can also see that that 30 amps is independent of frequency because it's an impulse. The amplitude of the harmonics are all constant. You can also see how the voltage goes along with that. You can see between the cursors, the impedance is relatively fixed because the current peaks and the voltage peaks both have all about the same amplitudes. And then once we get up towards around 100 kilohertz, you can see the voltage dips down. So we end up with a dip in impedance there. But that's one of the challenges is how are we going to measure impedance? And it's kind of interesting that it's going to force us to use time domain solutions rather than vector network analyzer solutions, just because we can't get enough source power to overcome noise. Ground loop errors also become a much bigger issue. Um, I think I've given a couple of papers last year on ground loop errors. And one of the things that I said is that ground loop errors are always there. The question is whether or not they're apparent. And they only become apparent when the ground loop error is about the same magnitude as the signal that we're trying to measure. And then it starts to get in the way. Beyond that, we can't see it. But now with these very low impedances, we are starting to see ground loop errors, even in things like our oscilloscope probes. And so this is just one example where we took coaxial cables and probes, and we looked at the coaxial ground loop error that's created just by the ground bounce on the ground planes at the printed circuit board. And here you can see that these ground loop errors, they're relatively large. There's only about 11 dB between the signal and the ground loop error. And so that doesn't lead to very good measurements. And so one of the challenges that we have is how do we deal with those ground loop errors? And the answer is that we need to build coaxial isolators into our probes. And in the meantime, while they're not built into the probes, but Picotest was forced to design coaxial isolators that were small enough that we could fit them on the oscilloscope channels. And so that's still a challenge, and the challenge is going to be increasing with time, but at least for the time being, we do have a solution. We have bigger fish to fry. So if we look at this image, this is kind of an interesting image, but the top waveform, that's actually a dynamic current waveform that we've created within the ASIC area. And this is one of the Picotest load steppers that's just creating this wave pattern. And there are different patterns that we're looking at to evaluate different things. So you can see the first pulses are exponential rise and fall, and they're relatively slow. And then the next pulse you can see has linear rise and fall. And then there's some sine waves. There are a couple of bursts. And then about where that center line is, the left cursor, you can see we have a pulse that goes from 1200 amps down to 600 amps, and then another step from 600 amps to 0. In the lower trace, we're just evaluating what the voltage does in response to these current changes. And we can see that in the lower trace, we can see that there's a resistive part of the measurement from the load line, so that when we get these pulses in current, we can see inverted pulses in voltage. But what I really want to focus on is the pulses between the cursors, where we went from 1200 amps to 600 and then 600 amps to 0, because you can see the two voltage responses in the voltage waveform. And even though they're not particularly clear at this point, you can see that those two responses are different. Here we can see a better picture of what those responses look like, and we can again clearly see that the differences between these two steps, same current, really different voltages. And this causes us tremendous trouble because one of the presumptions that we've always had in power integrity, in fact, the entire basis of power integrity analysis, was the assessment of impedance. And we tried to create a finite and fixed target impedance. So we would calculate what the target impedance was, and it's supposed to be flat. But here's the thing. If we had a fixed impedance and we generated a fixed current, we would get a fixed response. And that would say that each of these two responses would have to look identical because we had the same DI and theoretically the same impedance. But these don't look the same. And what that says is that our performance now is not linear. And it's also not time invariant, right? It depends on time. And in fact, Heidi showed a really great simulation of that at APEC this year. But It's impacted by where in time these transients occur and also by the magnitude of the step. But that causes all kinds of trouble. One problem is that everything that we use for the assessment of target impedance and even Bode plots for stability have the requirement that the solution be linear and also time invariant. And unfortunately, now it's not, which means that all of our interpretations fall apart. Bode plots don't work anymore because we're not linear and we're not time invariant. And the whole concept of target impedance doesn't work anymore because that's also not linear and it's not time invariant. So WTF, what are we supposed to do with this? And that is probably, in my mind, one of the biggest challenges that we're facing today. Now, we do have other challenges, and one of the ones that I hear about a lot is what do we do about measuring high-speed currents? So if these ASIC currents are getting faster, we don't really have tools for that. We have clamp-on current probes, and well, it's not so easy to clamp onto an ASIC, right? That isn't going to happen. And even if we could, they don't really have the bandwidth. And so it's forced us to look at different ways to measure current. One of the more interesting ones is the Sense picture that shows that near field integration works. And I published this, I think, first back in 2015. And this example is from a load slammer test, actually. And this was a load slammer on a Canyonville test board. And the Canyonville test board did this very large current step, and it does have a current monitor on it. And so we can see in the top trace, when the step occurs, we can see what the voltage response looks like. And in the second trace down, we can see what the current monitor looks like. Now, the question is, how could we measure that high-speed current without all of the intricate electronics that were required to monitor it in the first place? And of course, these waveforms aren't all that fast, so maybe not such a big problem, but things are getting a lot faster. So how would we apply this as the signals get much faster? And so in the red trace, the next one down, what you can see is that we used an H field probe, a near field probe, and we actually looked at the current in the printed circuit board plane, and we generated this raw waveform. That's the red trace. And then something magic happens when you integrate H fields because the integration of the H field is current, and we end up with that orange trace. And you can see that the orange trace looks an awful lot like the blue one. And so one of the things that we're saying is that, yes, we can measure high-speed currents, but we're going to have to do them very differently than we do now, and in some ways that are a little bit less comfortable to us. And that would mean doing near field integration, and that requires precision near fields and um, precision integration, which would generally happen within the oscilloscope. So the oscilloscope is becoming an even more powerful tool in PI. And you're going to see that there's going to be a lot of changes to oscilloscopes and the capabilities they have as they adapt to being able to accomplish more of these measurements. This still isn't really ideal, and there are other solutions on the way. And one of the ones that I'm excited about is that Tektronix just introduced a new probe called TICP. And the TICP probe is a galvanically isolated, very high common mode rejection probe that uses RF demodulation. And there's some benefits to that. One is that it gives us very wide bandwidth at a gigahertz. It does have really low noise, which is essential for our PI measurements. So it's got very flat response, very low noise, and very high bandwidth. So that means that we can measure current, but we can only measure current if we can measure across an accurate resistor. And so we need high bandwidth shunts in order to be able to make these high speed measurements. And so I think that's the next thing that's going to occur is we're going to see new developments of very high bandwidth current shunts. And I can tell you, Picotest is actively working on that now. We do have some that are very small embedded devices, meaning that they'll be consumables. You'll take this 80 mil by 80 mil chip shunt and you'll mount it on your board, and that will have test points on it so that we can accurately measure very high currents. One of the interesting things that we use that for here is so that we can measure the current in the shunt resistors in a very high speed load. And that's what this picture on the left is in the bottom trace. That's actually the voltage across one of our very high speed shunts in our high speed load transient. We also need to be able to float these measurements, and since TICP offers 100 dB common mode rejection, actually even better than 100 dB, it means that we can measure floating measurements, including high side gates, and our current shunt resistors are actually floating. And so here you can see another picture of those floats. Also, every once in a while in that bottom trace, you can see these really huge spikes that occur. There's three of them in this image. And what those are the crosstalk reflections when our 1,000 amp channel turns on in the load. So yes, everybody's worried about crosstalk, and this is a really good picture of how crosstalk appears even in our own transient loads. There are also accuracy concerns, and this is one that I had never really considered before. Um, And I'm not sure why, other than I don't think anybody questioned it. But using the same demo pattern that I showed before. So in order to try to keep this focused, we used a single demo board running a single demo pattern. We used one oscilloscope and we used the same channel of the oscilloscope for every measurement. So we removed an awful lot of the tolerance uncertainties by using the same scope and the same channel and the same demo board and the same load controller. We even measured on the same test point, but we measured that voltage response with a bunch of different probes. And when we did the statistics of the minimum and maximum and peak to peak voltages and the mean voltages, we ended up with significant differences. In fact, the differences in maximum excursion voltage was 17.3 millivolts. And in peak to peak, it was 10 millivolts. And for the minimum, it was 11 millivolts. And this is really problematic because we're saying, so we took different probes, measured on the same demo point with the same demo board on the same pads using the same channel of the same oscilloscope, and ended up with 17 millivolts of uncertainty. And for the purposes of our discussion, that's almost a third of our total allowable window. And that doesn't even include the tolerance errors yet of the scope channel to channel or scope to scope errors. This is just probes. And so one of the things that we're going to have to deal with is how do we deal with the uncertainty that's really large? And in our own measurements, what we noted was that in these measurements, there were two in particular that were really close together, in fact, within about 3 or 4 millivolts. And that was the TICP probe and the Picotest P2104 probe using a coaxial isolator. And what that would suggest is that a big part of this error is ground bounce error and how the ground bounce error gets into the probe measurement. So one of the things that I said earlier was that um, ground loop errors are becoming more significant, and the Picotest needed to make coaxial isolators that could fit on all the scope channels so that we can provide coaxial ground loop error isolation in order to improve these measurements. And I think this kind of confirms that, but it's really important that we understand and correct these measurement uncertainties because we can't really measure a 50 millivolt window with 17 millivolt uncertainty. It's just too big an uncertainty. Another thing that's happening is that as we measure these planes and even things like our measurement shunts and even capacitors, the ESLs are getting much, much lower. In fact, down into the teens of picohenries, maybe even lower than teens of picohenries. And so one challenge becomes how do we accurately measure 10 or 15 or 20 picohenries? It's really difficult. And that is creating new challenges for us. Um, I did actually show a presentation just about a week ago showing a new gap cap from Quantic, and we actually measured their capacitor ESL at about 30 picohenries, and they have one that looks like it might actually be as low as about 12 picohenries. In measuring our own shunts, you can see here, in these particular measurements, we're measuring our shunts at 25 to 50 picohenries. Those are going to go down yet again to about 12 picohenries. And so now we're facing challenges of how do we measure these inductances down to tens of picohenries accurately. And so that's challenging us in many different ways. One is that if you're like me using the Bodhi 500 for my measurements, that doesn't have the most intricate of calibration support capabilities. In fact, it doesn't support calibration kits, but we would still need to be able to not only calibrate the instrument, but fully de-embed the mount. And so that became one of our challenges this year, was to make a calibrator that was ideal enough to measure these picohenry uncertainties. Currently, we can measure about 3 picohenries using a matched set of calibrators and printed circuit board mounts, meaning that we calibrate the instrument using this calibrator, and then we mount the components on matching printed circuit board mounts, and then we can make measurements in that way with an accuracy of about 3 picohenries. We do think we're going to need to continue to improve that, but 3 picohenries is pretty small. We have another problem, and this is also another uncertainty, and that is that most of these power boards, the VRMs themselves, are programmable. And this gets into a lot of nuances, and it also gets into a lot of the reasons that we have these nonlinear responses and um, time variant and nonlinear issues that interfere with our measurements. That's kind of by design if you're the VRM designer, because they want to give us all kinds of tools to improve the transient. So they do have built-in nonlinear controls. In fact, most of these PM bus boards have hundreds of programmable parameters, including control loops and nonlinear elements and load line controls and all kinds of other tolerance things that we can program through the VRM PM bus. And that leads to two different challenges. One is when we program the PM bus, how do we tune that for optimal performance? And if we think we did, how would we prove that? And what happens if that changes? And how do we predict that? And how do we simulate that? So all of these things are kind of falling out of the fact that, hey, we figured out how we can make better responding VRMs. We just don't know how to analyze, simulate it, predict it, or even really excite it all that well. And if that wasn't enough, most of these still use PID, proportional integrated derivative control loops. But that's running out of steam too. And that's the reason that some of these PM bus controllers now include nonlinear control. But it's even going beyond that. 3 times this year, I've heard from companies that are doing state vector control. I even heard of 2 companies that are doing neural network feedback in their power systems. Think of that as AI for the feedback loop. What do we know about that? And how is that going to be enhanced? And how is it going to be independently optimized? And how will we simulate it? How will we excite it, validate it, characterize it? And so all of these challenges fall out of just the fact that we are able now to program these things that are going to improve our performance. We just don't really have all of the infrastructure that allows us to um, interpret and assess it. Then we get to cooling considerations. This is really interesting to me. One of the reasons it's so interesting to me is because I don't remember ever signing up to be a plumber. But if you walk into my home lab here, that's the first thing you see is 2 refrigeration liquid cooling systems, one on my left side bench and one on my right side bench. And almost everything starts with connecting the refrigerated liquid cooling system. And that's really different than it was even just a year ago. And it gets into a lot of our capabilities for both access and measurement that I talked about earlier. And it's also just a little bit more time consuming. And yes, occasionally these do spring a leak or whatever. And so it is another level of nuance. There's different ways to do to do liquid cooling. One of them is immersion cooling, and that's starting to become more popular. And that is you just take the entire electronics and you just dunk it in liquid bath. And that liquid bath flows typically at a very high flow rate in order to get turbulence so that it provides good thermal impedance. But it also obviously adds even yet another level of complexity in how it is that we connect our measurements to devices that are now underwater. Becomes really challenging to do this. And of course, there's not really water in there because if it was water, it would be growing agents and mold and bacteria. And so these are antibacterial liquids that are designed for cooling. But whether or not you're adding cooling manifolds or you're doing immersion cooling, however it is that you're doing it, it adds this new layer of complexity that's also between us and the ability to make measurements. And again, like I said before, unfortunately, these cooling systems block most of our access anyway. There's very little here that we can actually connect to. And if you happen to be a power electronics guy, you can see all of these power modules along the top edge and the bottom edge, and you can see it even in the top left and in the bottom right. There isn't really much accessible for us to be able to measure in that device. The inductors are included in that, there are capacitors in there, the drivers are in there, everything is in there. And the only connection to that power module is through the printed circuit board, which generally doesn't come out on the back side. So access to module measurements is really challenging and comes back again to how we measure currents. A lot of the measurements we need to make in these modules have to be done through near fields. Then we get on to VRM topology considerations. And that's a place where an awful lot is going on right now. There are so many evaluations for new topologies and techniques, and everybody's trying something different. The one on the left, that's one of the ones we did a year and a half ago now. And that was one of those big 14 by 14 inch boards. This particular one uses an analog devices module that's from Linear Technology. What's interesting about this module is it's single stage 48 volts to core. And there are a lot of pros to that and also some cons. It's really small. It includes a controller, a microcontroller in every module. You can see there are heat sinks built into the module, which I didn't particularly like. It makes them kind of tall, but it's single stage 48 to 12. I'm not sure exactly what this is, but I think it might actually be an LLC controller. One thing that we did note is that it took a tremendous amount of bulk capacitance in order to get to the impedance levels we needed to. In fact, that board on the left has almost 100 millifarads of bulk capacitance. And one of the big claims was that 48 volts direct to core single stage conversion. If we look on the one on the right, that's much more typical of what we see today. We can see there are two 48 volt to 12 volt bricks, and almost every major company makes those. They're extremely efficient. They're very high density. Each one of those modules can get to more than 1500 watts, and they typically are in the 95 to 98% efficient range, depending on power. So getting from 48, or actually data center is really 54, but getting from 48 to 12 or 54 to 13 and change is really efficient through those two modules. And then the major power plane between those modules and the ASIC is carrying 12 volts to the power modules, and then the power modules are buck step down regulators, and those step down from 12 or 13 down to the core of 0.7 or 0.8. And then on the right side, you can see there are a couple of switching power supplies that run the controller. And then there's a digital controller that runs 32 phases, 16 modules, and 2 phases per. This is kind of current state of the art, but it's not good enough. And there's discussion about, whether or not it makes sense for us to be routing this 2000 amps laterally from literally where the module is to the center points of the ASIC, you still got to carry 2000 amps through those planes. And does that make the most sense? Well, there are a lot of new assessments going on, and there are different techniques that we're looking at. One is TLVR, transinductor voltage regulator topologies, using um, an additional winding on the inductors in order to try to get better transient response. And it does work. This particular image is from Iram Ben Israel from Broadcom Israel. He was part of our presentation on design of core 2000 amp core power rails, and he showed this data from their own power buses. And he showed what it looks like for TLVR and non-TLVR control in the VRM. And he also showed how it changes using linear versus nonlinear controllers. And you can see that all of the responses are different. And it does show that the TLVR with nonlinear and linear controls improved the transient response by around 7 millivolts. And that sounds pretty good, but it also adds an awful lot of complexity, and it adds cost because of the additional winding in the inductor. And of course, all of the inductors have these windings in series. And if any one of those points in that chain breaks, we lose that board, which is kind of unfortunate. But what I want you to ask yourself is it worth it? And yes, we saved 7 millivolts, but if you go back just a few minutes ago, we said, and we're measuring this with 17 millivolts of uncertainty. So did it make sense to go to this added complexity to measure 7 millivolts if we might still be inaccurate by 17? And that's to be seen. Whether or not there really is any long-term benefit to TLVR, I don't know, but it is one of the topologies that's being thrown around, and we'll see whether it sticks. IVRs, companies now are trying to make modules small enough that they can put them on the package. There are even people looking to see if they can put power modules into the multi-chip module, and of course, there are even people looking at putting them on the die. Of course, they all have their own ramifications and repercussions. So as we get the power supply closer and closer to the ASIC die, we get more and more concerned about crosstalk coupling and noise. And of course, it would take up an awful lot of space to get 2000 amps of power onto the die or even onto the package. One thing that we're starting to hear a lot about is vertical power, and that says that, hey, if we put the power system on the back of the board instead of on the top, then the path gets a lot shorter. We only need to get through the printed circuit board, and so we can lose a lot less power going through the board if we go from the bottom to the top. And I don't know, I've given a lot of talks on that in the past year. And one of the things that I said is I'm hearing a lot more about it than I'm seeing. So there are people playing with it, but I haven't seen any data that says, yeah, it's really great. And if you look at the way that it's being implemented, it's really interesting. In this case, this is one of Analog Devices modules. And they took that module that you can see in the upper left-hand corner of the picture. That's one of their micro power modules, and they just put it into an array. So they made a tray of these little modules. And then there's an interposer board. You can see the bottom side of that tray, and that solders down to the back of the board at the BGA pattern. What's interesting about this, a few things really. One is that you won't find those modules on the Analog Devices website. You won't find the individual module, and you also won't find the tray. But what's more interesting is you'll see that the way that this is being implemented is always in a way where it does double duty. We can take that power module and we can mount it laterally on the top side of the board in a traditional way, or we can mount it in an interposer on the bottom side of the board. And so what you can see is that everybody's kind of hedging their bets. Nobody's really convinced that this is really going to be the path forward, but this allows people to play with it. So if you look around, I think what you're going to see is that there's lots of talk, there's lots of noise, but we don't see an awful lot happening. This also comes with added challenges. So we talked about the challenge of all this cooling, and now everything is water cooled, and some stuff is immersion cooled, but what if it isn't? So now we have the power modules on the bottom side of the board, and we have the GPU on the top side of the board. Now we need to water cool both sides. And the way that the rack works, there's a lot less room on the bottom side of the board than there is on the top side. So there's not really a whole lot of space for water cooling on the bottom side, which means we're almost forced to doing immersion cooling if we want to do vertical power. And so the whole idea of double-sided cooling becomes kind of controversial and also comes with its own list of issues. And as we continue to move towards more and more nonlinear control, the VRMs are going to get better and better performing and independent of the measurement access and independent of the cooling. We need ways that we're going to be able to synthesize this. How do we predict it? How do we optimize it? How do we simulate it? All of these tools are really at this point sort of non-existent. Done an awful lot of work on measurement of hysteretic control devices. And by design, the hysteretic controller is a chaotically controlled instability. And being nonlinear and being time variant, how do we simulate that using our simple state-based average models? That's not going to work. In the case of neural networks, it gets really difficult, maybe in time domain, but it'll be really heavily dependent on the programming control and also on the dynamic performance of the ASIC, which we generally don't know. And so we are starting to see a lot of interest. We are starting to see a lot of papers, but I kind of think that there's this whole infrastructure that doesn't exist, and that's going to be one of the bigger challenges. Within this, I think there's another big question, and that is where's GAN in all of this, right? GAN is lighter, cheaper, faster. I think I heard Alex Liddell, and he's one of my superheroes, but I think I've heard him say more than once that gallium nitride outperforms silicon in every major metric. And that's true, but it still hasn't found its way into low voltage DC to DC converters, certainly not on the core side. We're at 0.7 or 0.8 volts. And the reason for that is that the conduction, reverse conduction in gallium nitride isn't very efficient. Whereas we can get 0.6 volt diodes inside as the parasitic diode inside a silicon MOSFET. In GaN, that's more like 2 to 3 volts. And so during the dead time, the device becomes very inefficient. And so one of the things that people are working on, including me, is what are the topologies that would allow us to use gallium nitride in the low voltage core side, and how will that prove spatial efficiency, and how will that improve performance? We do actually have this demo board that we're using now in order to show off some of the key features, challenges, measurement techniques, and whatever is this 2000 amp board. If anybody's interested, these are in our demo pool. You can borrow them. One thing is that we can create different workflow patterns. So if we know what our workflow pattern is, we can program that much like you would program an AWG. It has pull down menus. The pull down menus allows us to choose from different waveform patterns as segments. So we can have a sine wave segment or a pulse segment or a step or whatever we want. And while we're creating this pattern, we can look at the currents, we can look at the input voltage, we can look at the output voltage, we can look at the output current. And well, of course, that means that we have all of the data to look at power lost and whatever. And we can look at that in a specific workflow. So if we can define the workflow, we can define the performance. And if we can define the performance, well, we can iteratively, I guess, control the PM bus to figure out where it is that the settings would be optimized for a particular workflow. If you happen to be a guy that's using something like ADS, it would be much like a cockpit optimizer where we say, okay, we want you to look at the peak voltage and the minimum voltage, and we want you to iterate the parameters in the P bus until you get the best performance, meaning the lowest deviation around the central voltage. And we can do that. We can evaluate large signal effect. And, for almost a decade, I think I've been talking about large signal effect, though we hadn't seen it in really big ways. But here's a really good picture of it. The reason that this occurs is that when we do a load dump, there's a lot of energy that's stored in the inductors on the secondary side, the step down side. This is the filter inductor. And if we just dump the load, then where does that current go? It can't go to the load. The only place it can go into is the bulk capacitors. And so the voltage is going to rise, and it's going to rise because we had to take the energy that was in the inductor and we moved it into the capacitors. But if we look at the ripple current in the inductor, it's not a constant number. That's a time dependent signal, right? It's a ramp that increases from the start of a pulse and it reaches a peak at the end of a pulse. And that says the amount of energy that's in the inductor depends on where it is within the switching cycle of the VRM. And for the first time this year, Heidi Barnes Keysight did that simulation to show what would happen if we did a time domain step and could move that step from the beginning to the end of a switching waveform and just be able to slide it from the beginning to the end. And sure enough, we ended up with a parabolic response that depended on where in the switching cycle we generated that transient. We can also generate different kinds of patterns. And one question is, how can we most efficiently measure impedance? I'm going to give a paper on this at SPI in just 2 weeks. And there are lots of different ways. One of them is called compact discrete multisign. Anybody that's here that's been involved with batteries knows that we use multisigns very frequently for impedance spectrography of battery health. But now it seems like it might have a place in power systems too. What looks like noise, just Gaussian noise, we can see the pattern we generated in the lower right. It kind of looks just like noise. But if we look at the FFT of it on the left in that red trace, what you can see is that there are finite sine waves embedded in that waveform. And we can embed as many of them as we want. You can see that they all have the same amplitude. They're all about 46 amps peak, which is healthy for getting over signal and noise. It's certainly a substantial signal. And then we can look at the coinciding FFT voltages that are in the blue trace, and those are extracted from the voltage noise pattern that was resulting from our current noise. And we can see that in the purple trace. And now we can get very accurate broadband impedance data, and we can do it really quickly. So this entire noise pattern is 1 millisecond. It's a single 1 millisecond acquisition. And in that 1 millisecond, we can generate an impedance plot from 1 kilohertz all the way up to about 20 megahertz. And that allows us to do it really quickly. And more importantly, because I'm lazy, it means I can do it without having to connect my refrigerator. We can use that same pattern to generate efficiency curves. And here you can see we're just doing steps in current, just kind of a staircase pattern. And we can look at the input voltage, input current, and output current. We do the mathematics in the scope. That bottom red trace is the calculated efficiency. And you can see it relatively low currents on the order of, maybe 100 amps or so. We actually hit about 90% efficient. And you can see down at the end, the rightmost cursor, we're down to about 69% efficiency at 2000 amps. And so we are developing tools that allow us to get the data. What I think we're still going to be missing is how do we interpret this new data? And so with that, I want to thank you for attending, and we do have time for questions. Yeah. All right. So the first question, this is one that's really controversial. So what extent do backside power entries solve or reduce? We don't have a lot of really solid data on it. There's a lot of people talking about vertical power and many fewer of them doing it. Certainly doing the simulations of how much power do we save on the lateral planes isn't that hard to do. But of course, it's also heavily dependent on the design of the vias for the board and also the design of the lateral planes. So we can kind of control the answer, which makes it not all that helpful. Also, as we shrink down the modules so that they fit on the backside of the board, they also tend to get less efficient. So I personally haven't seen any papers yet that say that there's really a significant improvement in lateral power. In fact, we did a panel at DesignCon, and the panel was supposed to be very controversial. So we invited people that were big believers in vertical power, and people that were really opposed to it, and people in the middle. And, for myself, I'm saying that I don't really see the benefit, but I'm open-minded. We thought the one that was going to be most pro for it was going to be Google. And Google's presentation said they have some interesting data, but there's really nothing conclusive, and it's probably not all that. And so I haven't seen anything yet that says there's a huge benefit to it. IVR, how can we ever measure it and optimize it? Well, that's one of the things that I talked about in this session is access is so limited. It's really hard for us to tell much of anything. Some of these GPUs do have data streaming on die, and so it is possible that in some cases we're actually going to be able to get the power rail data from the ASIC, and it'll be able to spew data. Some of my customers can do that. A lot of it we just can't really see, and that's the part that scares me. Much of what we can get is from near field measurements. And near field measurements can be a lot more powerful than you think. Now, there have been a few cases, even this year, where I've been called on to make a model of a VRM that we didn't know anything about, black box measurement. I was called on to make a simulation model of the device using nothing other than near field probes. And I was able even to get the turns ratios of the transformer. I was able to get the inductance of the transformers. And so with powerful enough antennas, you can get an awful lot of data, but how we're going to get it going to be really difficult. How we're going to optimize it, I think the only way to optimize it is going to be in a closed loop system. The oscilloscope will be monitoring something that represents the data, and the same oscilloscope will be diddling the PM bus. And what we're going to end up doing is iteratively controlling the PM bus in order to get the best response. That'll be valid for a workflow. Michael Margulies, Infineon is starting to release gallium nitride with integrated Schottky body diodes. Yes, I did see that, and that is exciting. And I think it really is important to get gallium nitride into the low voltage converters. And I think if we're able to do that, we will be able to get smaller and more efficient. Even more importantly, we'll be able to get to much higher um, frequencies, which I think becomes even more important. I can tell you, I am working on gallium nitride implementations of low voltage myself, and I do believe that we will achieve 13.5 megahertz switching regulators that are completely gallium nitride and without body diodes or Schottky diodes, and it will be scalable to 10,000 amps. I haven't published my topology. I don't know if I will, but I can tell you that we are actively working on that development and getting gallium nitride into the power system. That really is an essential next step. For those of you involved in EMI, you probably understand why it is that I chose 13.56 megahertz and not 10 or 15. But 13.56 megahertz is the scientific band, which doesn't have any EMI requirements. So we are allowed to generate all the noise that we want at 13.56 megahertz, and that minimizes how much power we have to lose in trying to filter noise. And I think that there's going to be an awful lot of benefit to doing it. I actually developed this topology almost a decade ago, just never proved it. And I think it's going to be interesting to see, but hopefully in the next year we're going to prove that the topology works, and then we'll have a path forward with gallium nitride.
Okay, I think we're good. Well, thank you very much, everyone, for joining. Thank you, Steve, for presenting. It was really great. I will send the slides and recording this afternoon.
Thank you. Thank you for having me, and thank you to all of you that attended, and have a great rest of your day.
Bye-bye, everyone.